Hello, welcome to this video on the Datum Telescope, or otherwise known as the Plane Telescope. Today, this video will be mostly on the operation of the telescope, and it's come about because of several points, some more major points. The first one is I really needed a video to explain what's going on with this telescope, because I've had a lot of interest and a lot of emails, and say repeating myself in emails, I thought I'd just make a video, and that way put it up on YouTube and everyone can see it. I'm getting a lot of interest from astronomers. The new concept of this telescope has sort of tweaked a few things there. I still have my flat earth measurers, but also I have telescope manufacturers interested. As the telescope is now at operational stage and is completed, all proof of concept have been proven, so the telescope is now actually operational and can be manufactured. Also this, I might briefly mention again this optical trajectory. Everyone seems to be interested in that. That's this, basically the astronomers are quite interested in that. I didn't realise they would be. They need an accurate optical pathway. Also I'll do a quick demonstration of that in this video as well. Also we'll talk a bit more about future of telescopes as less glass and more cameras. Telescopes are going to become smaller. There's a new lensing coming out with going to carbon. So we're using diamond. I think that'll come in soon. Diamond lensing. We'll be able to actually even be able to control, possibly at atomic level, the lensing. That's sort of future. More portability is a really attractive. I've been having a lot of interest in that, this portability of this telescope. And also long length and just using a primary lens. So that is another thing that these astronomers are also interested in, which again I never thought about. But they look to having as less glass as possible, which is understandable because it's cheaper. And these new cameras are coming out now. They're just getting more and more sophisticated. So the day will come when glass will be removed from telescopes. I predict anyway. That's my opinion, and I'm going down that path. So also we'll do a really close up of the telescope, and we'll be able to zoom in on certain aspects of it, and that's probably what everyone really wants to see anyway. So the sooner we get this done, the better. Let's go. Alright, we'll just talk a bit more about this optical trajectory. Now I'll be trying to be brief because I have explained this in two other videos of mine, especially that video on the spinning barrel, gun barrel. That's really went into detail there. But basically the optical trajectory means is transmit angle of direction trajectory. Now what that means is all optical systems, I believe, that I've come across anyway, have an inherent small error, and it's basically this. If you take, for example, theodolite, which is more or less just a spirit level with a sighting device on top, and when we think it's dead level and we sight to a known to get a reference, but what happens then when we turn the optical sighting device over 180 degrees, the image at the other end changes slightly, giving us this error. So that is what I was discovering was my problem when I was doing these flat earth measurements. I was getting quite a consistent error in my measuring systems, and that's why I had in fact go to invent this new telescope to eliminate that. Because what happens with gun barrel sighting, telescopic sights, is basically we never use the optical reference. We just shoot a bullet, say at this rabbit, and we miss it, but the bullet ends up here. So what we do then is we just say, oh, that's where it should have aimed. I'll put the crosshairs here. That's where it was wrong. Now that's wrong. You can't do that. You must go the other way. You must have a true optical path, and then you can actually find out where your gun is shooting off. So In the flat Earth measurement realm, it become very inherent. For example, if I had two posts that were 2 metres off the ground, exactly, and I was to, the true optical path is this pathway in green. Now, if I had this slight error in my optical system, I could be measuring below the post or above the post, as in red. So that was my problem all along, and again the telescope eliminated that with this new being able to turn the optical system around. I'll just bring in the telescope now. I won't go too much detail into it, but just have a quick look at that mirror system. So let's just bring it in now. Okay, here we have the telescope and how it will look in production. This is there'll be a few modifications later on. We're using a 114mm lens at the moment, mirror at the moment, which seems to be the standard, which is based on the Bedford Lake experiment, which I'm trying to keep everything consistent, because that's what I'm sort of, with my flat Earth measurements, trying to do. Telescope's basically 1.2 metres long, and there you'll see the focusing assembly and a mounted camera, a 4K camera on the end there. These cameras can be changed to any size or whatever is desired. Of course, the major feature of this telescope is that the mirror can turn, and we have this physical datum point here, which is an extremely accurate point, and the optical pathway or the trajectory would be from this point here through the centre of the mirror to the far distant end, and it would become this green line, which will be derived by the fact that we can turn the mirror around, find the high and low points, and then come back to the halfway position. Okay, I think we've had enough on that. Let's go and have a look at that practical demonstration of how we eliminate this and get the true pathway. If you remember, the first video I had on the Datum Telescope was a picture of, was a long distance shot of our communications tower, Black Mountain Tower, which is about 17 kilometres from here. And just that slight error of a few millimetres, or 1.2 millimetres or something, I think, in my mirror, created 10 metres at the far end. So therefore, let's say 2 millimetres, for example, error at this end can create over 17 kilometres, 10 metre error. Now, that is an incredible. If you're trying to measure stars or to any physical point, you have got no hope unless you can eliminate this error. Okay, let's go and do the experiment. Okay, now here we have the telescope looking at our remote communication tower, Black Mountain Tower, through my lounge room window. What I'll do is I'll just zoom over to that communication tower now and give you an idea. Roughly, this is how the eye sees it at the moment. And here we go through the zoom of the camera, which is about the limit of this camera now. There we go, there's our tower. Okay, now I'll just zoom back. That's magnified, but there's the naked eye view. Now we just go back to our motor. And I'll switch on the drive. And you can see the motor turning slowly in a clockwise direction. Roughly a 1 minute revolution. The half moon section on that cog is the upper and lower high points of the mirror, which can be adjusted through that brass screw, and a clutch arrangement can be turned manually. Alright, next shot we'll go to now will be the magnified image through the telescope itself. Okay, here we have a little bit of video through our 4K camera.
a little bit soft at the moment. It's just going in and out of focus. I have a fair bit of wind buffering on the telescope, which is probably buffering the lens a tad, but that's what 4K would look like at 17 kilometers away. There's a fair bit of wind here at the moment, and those distant trees, so the air is not real still and there's quite a lot of disturbance in the air, so I don't expect it just see that drifting in and out of focus. Very hard to get this on terrestrial at this time of day. Okay, I think that's enough. Here we have a screen dump of the mirror at its bottom part of the cycle. Mouse coordinates 558 is the top of that line, that bar. I've also included in the screen dump, luckily, was the crosshairs from the Windows camera view. So that just should give us a little bit extra to centre this exercise. Again, now here's a screen dump of the mirror on its upper position of the cycle, and you can see it's moved quite a distance with coordinates 212. Here we have the mirror now positioned midway between the upper and lower limits at coordinates 385. We just have to exactly line up with the horizontal crosshair from the Windows 10 camera view. Now to fully align that telescope, we'd have to obviously do the X coordinates to lock the mirror, the light beam, to the boom of the telescope. Right now we just have a virtual positioning and not a true world positioning because the X coordinate.
From those three still shots of Black Mountain Tower, we were able to see the distortion in the mirror, giving us our upper and lower limits, roughly 10 metres at the far end. And we were able to reposition the mirror in the centre position to give us this centre line here, the green line. And that was achieved by this very slow motor. We was able to turn the motor, the mirror very slowly. You'd never be able to turn this by hand to give you that accuracy. That's why I installed the motor. The slightest movement, even a breath of air on this thing would put it out. So look, I might go this a bit further. People having trouble with this, both the flat earthers and the non-flat earthers and astronomers, they're really having, this is a very hard concept to get across, so I'll get a little bit more detail. I hope this will explain it even better. I've taken off the mirror from the telescope to help better explain this. Again, our extremely accurate datum point comes into this by now we can draw a very accurate point here, and now we can actually make this also 2 metres exactly to the micromillimetre off the frame of reference, which would have been, if we were doing flat earth measurements, would be the water level or any position, terrestrial position that you consider a reference. And what we did, we were able to now fix our point here and tilt the mirror up and down to get that centre line. So our beam now will be exactly in the centre and it won't move up and down, creating an error at this end, making this move up and down. So virtually what happened was we have removed, the telescope was just a virtual frame now. I can draw it in as blue. The telescope framework is nothing. It's just a virtual point that locked this mirror here and this position. This telescope framework can move up and down. It doesn't matter. It's irrelevant as long as this line now, this true trajectory, the trajectory point, is dead straight. So that's what we've tried to achieve. A very straight optical pathway. This section of the video will be talking about the future of telescopes. And to talk about the future of telescopes, we just have a quick history into the history how they developed. The first telescopes were developed to magnify a distant image, and it consisted of two lenses, a primary lens and a secondary lens. The magnification, which is what everyone was trying to achieve, was the focal length of the primary lens over the secondary lens, which roughly, if this was 1000 millimetres, this was 10 millimetres, you get 100 millimetre magnification, which was extremely good for early telescopes. The big issue was this exit pupil distance, which is when we try and extract the image from the secondary lens on the eyeball, and that's where telescopes evolved, all about the eye. So if you look at the mechanics of an eye, in the centre of the eye you have the macula, which is roughly a sensitive area of 2 millimetres by 2 millimetres, and that's where all our vision is done. The outside of the retina of the eye is lower density cells, and they have less megapixels, if you like, and that's all done by software. Your vision is actually done by software rather than your brain computes it. This part here is all the juicy bit, and that's where cameras are actually going. Cameras are going, it's all about camera technology now. If you look at your mobile phone, it's all about megapixels, size and light sensitivity. So what cameras are doing, they're getting smaller and smaller, and the camera sensor, which is a section of the camera, if you look at a typical camera sensor, this section here, they're getting smaller and smaller, and they're trying to approach this macula size. So in the 2 millimetres by 2 millimetre section, you could have one day 100 megabit sensor that is prone to noise, immune to noise, and extremely sensitive to light. So that is not too far off, and possibly 5 years ago you would have laughed at this comment, but now in your pocket you probably have a mobile phone with at least 16 or maybe 13 to 16 megapixel camera, and the sensor in it will be a lot smaller than the one here. Okay, so how does that affect my telescope design? As I said, I do not have a secondary lens. So basically, if you look at my arrangement, I have a mirror that brings in light through a parabolic mirror. The light comes in at right angles and it's reflected onto a sensor, which is a camera, which is 4 megapixels. 4 megabits. And let's, for example, say the CCD, or the sensor in this camera, is 4 millimetres by 3 millimetres. How do I work out the magnification of this lensing arrangement? Well, there's a wild card now, because we can't use this formula anymore, because we haven't A, got a secondary lens, and B, this is a new technology. This is just happened. So what I've used my clean formula for a start, because it's just to give you a rough idea, and it roughly goes like this. It's the focal length of the primary mirror, which in my case was 1200 millimetres, and divide it by the diagonal of the CCD array. So if that little CCD array was 4 millimetres by 3 millimetres, the diagonal would be obviously 5 millimetres. So my case was 8 millimetres times 0.95. Now that 0.95 is because we can't achieve unity, and the telescope ends up having a magnification of 142, which is with 4 megapixels. Now, this is where it gets weird. With 4 megapixels, I can achieve this formula. But as you increase the megapixels, this 0.95 actually goes away, gets closer to unity, 1. So we'll soon get to 16 megapixels, which will be roughly the resolution of the eye, the macula of the eye, and that's not far off, I predict. We will be there soon. Now, what will happen is you'll take this image on from your 4 megapixel camera, and you'll go stick this on your 65-inch colour TV, and you'll get another magnification effect. Now, right now, TVs are roughly, 4K, but there's 8K cameras coming out, 8K television sets coming out, or monitors, so you'll even get more magnification as the pixel density gets higher and higher. So one day you could have, the formula now is out the window, it could go anywhere. You could have, we could one day achieve 100 megapixels in a CCD camera array of roughly 2 millimeters by 2 millimeters, and we might be displaying that on a 100-inch television set with also a 100 megapixel resolution. So what will the amplification be then? I don't know. But right now, if you just want a rough rule of thumb, use my formula. If you want to go down this path of using CCD arrays, just the focal length divided by the diagonal times this 0.95 factor. Right, I think there's hit this home a bit, I'll just show you a few shots of a couple of these, where I'm going with these, using a smaller CCD arrays and what was happening. It's quite interesting, so I'll do some shots on that as well. So here we have the current technology in CCD arrays. On the left is a 20 megapixel out of a high quality camera, 2 small 1 megapixel from spy cameras from eBay in the centre, and a typical 10 megapixel from a compact camera on the right. Interesting, those 2 spy cameras, I was using them as they had a very small light blocking footprint, and they were, I believe this is the way the technology were going. You see, I've already mounted one there to try it on the telescope, but unfortunately the magnification, although it was should have been theoretically high, that 0.95 factor only works for 4 megapixel cameras. If we go down to 1 megapixel cameras, it comes down to about 0.2 or something like that. So anything less than 4 megapixels is virtually useless. I'll just zoom in there on that CCD array just to give you an idea of how small they are and how small they're becoming compared to that match. And I believe that's the way things will actually go. And this is, we certainly set the future for telescope design. Collimating the telescope is pretty simple. I'm just using a laser level with a cross hatch generator going through the centre of the telescope. To the centre of the mirror, to the centre of the upright post, back, and reflecting straight into the camera lens. We'll go into more detail now about the telescope itself. The telescope is built on a 50mm extruded aluminium platform. The mirror cell was built from 100mm PVC sewage pipe fittings, and just fits perfectly this lens cap comes off. And believe it or not, it was perfect size. The bearings are mounted at this point here, but if I was mounted higher, I could actually accommodate this larger mirror, the 200mm mirror. And in fact, just by extending this extrusion a little bit more, I could take a 300mm. And it looked like the flex in the extrusion had no problem at all with a 300mm mirror. I noticed as I was developing this telescope, I was a bit concerned about this mirror design, and I came up with a lighter mirror concept. So if anyone's interested in talking about that, but there's no reason to mount these things on glass anymore. These could be made another way and just as accurately. So I don't know why people are doing it with glass, mounting these mirrors on this heavy glass platform. There's another way about this. The mirror cell can be finely tuned by these screws at the back here, which will allow me to toggle the horizontal and vertical axis slightly. As you've seen them before, the motor drive, I don't think we'll go any further with that. Quite cleverly, I thought this one up myself. Unbelievable, this PVC series pipe fitting made a perfect mirror cell, and I can actually use everything, even use the inside here, I even use the O-ring, which is used as the compression washer for this back plate, which allows for the mirror to be tightened very hard against a strong non-movable medium, which I found the other telescopes that I had were spring-loaded, and just a movement in the car would jolt them into becoming out of collimation. Okay, we'll move on now and just move along, and we'll see a bit more of the focusing mechanism. Here we have more detail of the focusing mechanism. The focusing motor is controlled by the same control box, which is a simple switch up and down to control both the mirror motor and the focusing motor. The focusing assembly sits on the production model, will fit on this floating platform that can be positioned anywhere along the beam of the telescope and accommodate any focal length of the mirror. The focusing is actually done by adjusting this lead screw, which slides this plate here backwards and forth, and it can be adjusted manually. I have allowed for a manual adjustment, but it's almost impossible to adjust these things manually. Over a magnification of 100, CCDs are very hard to focus, unlike the human eye, which is a little bit more forgiving. So the gear ratio of this is incredibly high and very slow, but it gets the job done, and very accurate with minimum disturbance to the telescope itself. The camera I have mounted here, which can be any camera and can be adjusted to any height depending on this beam, this vertical beam. Ideally you would love to have those small spy camera profiles which have virtually zero footprint on the light blocking, but this one is quite a large light blocker, and it does deteriorate the image quite a bit, but it gets the job done for this demonstration. And of course there's no need for a star aligner or a aligning scope, because if you were to see those other videos, the first video, the centre of this telescope, the boom, is the most accurate kaleidoscope to zero in on a distant star or a remote terrestrial object I've ever come across. So there's no need to mount any external spotting scopes or alignment scopes. Okay, I think we'll just talked about enough, and from this you'll be able to answer most of your questions that you've come in from. So we'll just do a summary now. Right, hopefully that video has cleared up a lot of questions. And my apologies for those people I couldn't get back to, but obviously now if I just send you this link to this video, it'll answer all those questions, the ones I've been subjected to. Telescope manufacturers, yes, there's a little bit of interest there from me for my telescope. I would like to hear from lens manufacturers. That's, I think I can contribute there with my new lens design, a lighter, thinner lens. Amateur astronomy clubs, they are really interested in this mirror mounting concept. I didn't think that would be, again, I just throw something out there and surprising what comes back. Yes, that mirror on the bearing is very simple. It's, as you can see, it's very sturdy. It's extremely easy to calibrate. It's sort of self-calibrating, and the portability factor I think you'd like too. The fact that you can just undo that mirror and take it away and put it in a soft padded case. Also, your questions about the length of the boom or the beam of the telescope. Yes, it can be, sorry I should have mentioned that, it can be sectionalised. I have experimented with some rigid centerpieces, so it virtually can be cut in half, and there's no reason why it could not be extended to at least 2 metres, 3 metres. It really has that potential. It's very rigid and strong, and for those people who actually asked about, who wanted getting into prime lenses to remove all other lenses and this one a very long telescope, yes, I think it can be achieved. I've sort of been writing to a few telescope camera manufacturers, and I've sort of been holding off until this video, but they know what's happening. There's no doubt. They're switched on. They know where this next movement in telescopes is going. It's going into the camera. Expensive eyepieces. You can spend $300 or $400 for an eyepiece now, a really good eyepiece, and a camera will solve that problem for the same price, and you can use that camera for whatever. So that's the way they're going. So obviously this is a simple, low cost and not astronomical in price. So something to think about, and please contact me on the email after this video if you're interested in, I haven't answered any questions. So thanks again for watching this video.